So, well, last lecture, I already upload the video on YouTube. So for the last lecture, so if you want to review, then you can check out the YouTube video. Okay, so now this time I'm going to talk about EPRL model. Yeah, so I hope you all know these three guys. Hopefully you know their names. So Engel, Pereira, Rovelli, Levin, yeah, EPRL. All right, so okay, again, let's start with classical theory. Yeah, and the classical background behind EPRL model is Plibansky formulation of general relativity. Plibansky formulation of gravity. Okay, and you can write down the Plibansky action. Okay, so the Plibansky action of general relativity is very simple. Let's again consider physical dimension to be 4, and so this is the Plibansky action. So the first part is just like a BF, but now for our purpose, we add a twist. So by twist, it means that we twist a little bit, make a internal rotation of the B field in the joint representation. Okay, and we introduce a parameter gamma, which is a Barbero-Emis parameter. Barbero-Emis parameter, and then wedge Fij. So here Ij is I and j goes from 0 to 3. Yeah, so they are Lorentz covariant index, yeah, internal index. So Ij index, and it is antisymmetric I and j. With I and j, it means that B is evaluated in SL2C Lie algebra. It's SL2C valued two form. And then there's so the first term is just a BF action. Yeah, twist a little bit with B, and there's a second term, and there's a phi field which is a Lagrange multiplier. Bij wedge EKL, and that's it. This is the Plibansky action, and so here, as I said, so Bij and Fij. So Fij is just a curvature. So they are SL2C Lie algebra valued. So that is different from previous BF theory. So last time we only talked about BF theory with SU2 Lie algebra, and now it is SL2C Lie algebra. Yeah, and the idea is simple because the gauge group of gravity in 4 dimensions is Lorentz group, so SL2C. Okay, so this phi is the Lagrange multiplier. Yeah, and it satisfies certain constraints, satisfies certain property that this phi ij, phi ij KL, and ij and KL, they are both antisymmetric. Yeah, and also phi ij KL equals to phi KL ij. So yeah, if you switch 2 indices altogether, it is invariant. And also it satisfies a traceless condition. If you contract IJKL with epsilon IJKL, you get 0. Okay. So this is some symmetry property of this phi Lagrange multiplier. Okay, and okay, so as I said, this Fij equals to Fij of certain connection, and this connection is of course SL2C Lie algebra valued. So F is the curvature. Then if you study this classical theory, compute the variational principle, to variation deriving equation motion from the Plibansky action, then you can check by yourself. that you get Einstein equation. Einstein equation, and in that case, this Lagrange multiplier phi will become the Weyl tensor in general relativity. All right, so in this sense, this classical Plibanski formulation of gravity is just on-shell equivalent to usual Einstein-Hilbert action. So this is classical setup, which is equivalent to usual Einstein gravity. So now let's look at the quantum theory by formally write down the path integral. Now we have three kinds of fields. We have B field, we have connection A, we also have this Lagrange multiplier. Yeah, formally we can write down the path integral where Plibanski LP means h bar times LP square means h bar times g Newton. Now you see this Plibanski action, it is linear to phi because this phi is just Lagrange multiplier, so you can easily integrate out phi. Okay, integrate out phi. Now you can integrate out phi, and what you get is a delta function in the path integral which impose certain constraint, and what we call simplicity constraint. And this simplicity constraint, this is a key constraint, a key ingredient in Spinfoam construction. Okay, so you can write down this simplicity constraint by you just variating or making derivative of this phi to the action, and what you get, the simplicity constraint is given by the following: so epsilon mu nu rho sigma mu j rho sigma KL equals to the volume KL. Okay, so it is linear to phi, and apparently, if you integrate out phi, you will get the factor b wedge b equals 0. Yeah, you may wonder like that, but because phi satisfies this constraint, so what you get is actually this b wedge b equals to something proportional to epsilon if you make derivative of phi. Yeah, so you will get this formula, and here v is just a function of b is 1 over 4 factorial epsilon j KL b. Okay, all right, so this is the simplicity constraint, and then well, there was huge literature study simplicity constraint, classically and quantum mechanically. Yeah, and so right now we are talking about classical simplicity constraint, and you can find the solution of this equation. So here I just give you the result of the solution. Yeah, the solution of simplicity constraint actually relates the Plibanski gravity to host gravity, Platini host gravity. Yeah, so solution of simplicity constraint, there are 3 sector of solutions. Okay, and so sector 1, it just says that there exists a cotetrad field E such that Bij equals to plus minus EI wedge EJ. Okay, this is the first sector, and second sector it says the same thing. There exists a cotetrad E such that Bij equals to plus minus the dual of E wedge E. Okay, and then there's a third sector which is degenerate, which is less interesting. It means that it corresponds to some degenerate geometry. It means that the volume equals to 0. So you can, well, you could try to plug in this formula, and you can easily check that indeed the simplicity constraint is satisfied if you plug in B equals E by G or epsilon E by G. And you will see if you plug in the expression of volume, you see indeed you get the volume element. Okay, so this is the solution of the simplicity constraint. And then if you you can also look back to the Lagrangian. If you say B equals to E by G or epsilon E by G, this action just reduce back to the usual Platini host action. So there's a Barber-Emis parameter. So there's a twist of E by G. So it goes back to the host action, actually. All right. So then when we integrate our B, we get the delta function. So delta function of simplicity constraint. So what you end up with is dA dB, a delta function of simplicity constraint. Yeah. And e to the ILP square. Now, because you integrate out phi, what you get is, well, on the exponential, you only have this BF part. So integral for E ij plus 1 over gamma star E ij Fij. Okay, so in this sense, we say that gravity is actually a constraint BF theory. So from the path integral, you see on the exponential, the action is just BF theory. But in the path integral, there is some modification of path integral measure because there's a delta function of the simplicity constraint. You are not, it's not a free integral over all the A and all the B, but subject to some constraint of the integration. So that's why we say gravity is constraint BF theory. Okay. Now this is more or less a classical theory and a little bit of a formal path integral quantization. Okay. So now what we're going to do is a little bit different quantization. It's not the traditional path integral quantization of gravity. We are going to do something called Spinfoam quantization. That's the way I would call it. Okay, so let me introduce the scheme of Spinfoam quantization of gravity. Okay, so yeah, one punchline is that this is not precisely a traditional way of quantizing gravity, and because this is a traditional way of quantizing gravity is not really what we want. Because if you quantizing traditionally and Einstein-Hilbert gravity, and what you will get into trouble, like non-renormalizability and the UV, the bad UV behavior and so on. So traditional quantization of gravity is not really what we want. We want something else. Yeah? So Spinfoam quantization is a candidate for this something else. All right. So now Spinfoam quantization is based on triangulation. Yeah. So firstly, you need to introduce a so let's say Spinfoam quantization on simplicial complex. Complex in 4D. Okay. So firstly, we instead of putting this Bribansky path integral on the entire manifold, on the entire full manifold, we only look at this path integral inside the single full simplex. Okay. So let's put this this path integral in a single full simplex. Okay, and we expect the result to be the vertex amplitude, the Spinfoam vertex amplitude that I introduced schematically last time. The result is the Spinfoam vertex amplitude. Okay. Secondly, is that we are not going to precisely put this guy in the 4 simplex. So instead, we are going to first quantize BF theory. We are going to first forget about this delta function of simplicity constraint and quantizing BF theory. So firstly, we are going to quantize just the BF theory. Okay. So now in the 4 simplex, what we're gonna compute is schematically this kind of path integral e to the where this yeah, this is the quantity we are going to compute, and I mean we did compute that already. Last time we talked about this BF theory. Yeah, although it was SU2, but schematically here you get very similar result. So the result is a partition function or an amplitude of BF theory depending on certain boundary data. Yeah, because this path integral, we just put it on, sorry, this is not entire M4, but on a 4 simplex. We put this path integral on the 4 simplex, and then, yeah, 4 simplex has a boundary, and this path integral depends on the choice of boundary data. Yeah, so here, the boundary data will be, yeah, remember, for the BF theory, inside the 4 simplex, you get 15J symbol. And then the boundary data are those spins and intertwiners. So here, the boundary data are also spin and intertwiners. Or more precisely, the space of boundary data will give you a Hilbert space. Boundary Hilbert space. Yeah. So boundary Hilbert space is just the Hilbert space of boundary data. Yeah. So for the SU2BF series, the boundary data, the Hilbert space of boundary data are just the Hilbert space of spin and intertwiners, which are spin networks. It's a Hilbert space of spin networks. So this is our boundary Hilbert space for BF theory. 3, okay. So now this is just BF theory. We need to put a constraint. Yeah, we need to put a simplicity constraint, but now we put it afterwards by quantizing simplicity constraint. Quantize the simplicity constraint. Yeah. And impose to the BF Hilbert space. BF boundary Hilbert space. Okay, and the constraint will restrict your Hilbert space to a subspace. So then it give a restriction to BF boundary data, to boundary data. Okay. And then the Spinfoam vertex amplitude is just given by the BF amplitude with a subset of boundary data satisfying the simplicity constraint. Okay, the amplitude, the Spinfoam vertex amplitude, I call A of V, is just given by this partition function or the amplitude of BF, yeah, with the boundary data. Yeah, those boundary data satisfy the quantum simplicity constraint. Okay. So schematically, this is the way to construct the Spinfoam vertex amplitude, or at least in the EPRL story. So now let's come to make it more explicit. All right. So firstly, what is the BF boundary Hilbert space? So let's again recall SU2 BF series that we talked about last time. SU2 BF series. BF series. So we know the vertex amplitude is just the 15J symbol. Is this spin network with 5 intertwiners. J1, J2, and so on. Okay, and this is the 15J symbol. Okay, and then it is a dual diagram of 4 simplex. It means that for each intertwiner, it corresponds to a tetrahedron. Yeah, so it is also our usual logic of spin network. Is that for any vertex, it corresponds to a tetrahedron. Yeah, let's say a 4-valent spin network. Yeah, it's the intertwiner are quantizing the shape of tetrahedra. Okay, so it means that for each boundary tetrahedra of the 4 simplex, tetrahedron. Okay, and there is an intertwiner, IA, A from 1 to 5. There are 5 tetrahedron, and there are 5 intertwiner. And then, so there are triangles, boundary triangles of the 4 simplex. Remember, we talked about the topology of the 4 simplex. So there are in total 10 triangles. Yeah, and given by for any triangle, there is a spin. I will call JAB. Yeah, so A is smaller than B. Yeah, because any triangle is shared by 2 tetrahedra. So that's why I label J by A and B. Yeah, so in total, 10 triangles and 5 tetrahedra. Okay, so these spans, this give you the boundary data of BF series. So they are at least for a single 4 simplex, the boundary data are given by 10 spins and 5 intertwiners. Okay. So now this boundary, so the Hilbert space for this boundary data are just given by L2, the Hilbert space. You can extract the Hilbert space, boundary Hilbert space. The boundary Hilbert space is just the Hilbert space of boundary data. And yeah, each choice of the boundary data is a state in this Hilbert space. The boundary Hilbert space is just a L2 of SU2 power 10. Yeah, so they are in this spin network. There are 10 edges, dual to 10 phases, and the modular gauge. So basically, the boundary Hilbert space are just those gauge invariant states in the L2 Hilbert space of SU2, 10 copies of SU2. Okay, so this is the SU2 BF series. So now let's upgrade to SL2C BF series. It's complete analog. Okay, and well, the reason is that for gravity, or for Plebanski gravity, we are interested in SL2C valued BF series. But the structure is very much the same. So now it's the vertex amplitude is still 15J symbol. That's because all the derivation we did last time applies to any BF series of any gauge group. So the vertex amplitude is still 15J symbol, but now these J's are not anymore SU2 representation, but SL2C unitary irreducible representation. Yeah, so that's the only difference. And then the boundary Hilbert space is not anymore L2 space of SU2, but L2 space of SL2C. So the boundary Hilbert space space is just L2 SL2C of 10 copies of SL2C modulo gauge transformation. SL2C gauge transformation. So these are again some spin network states. Yeah, but the difference is that now it is a spin network state of SL2C, not SU2. So namely, so here for the boundary data are for tetrahedron. So there are 5 tetrahedron. So now there are SL2C intertwiners. For there are 10 triangles. The SL2C representations, EREPs. Okay, so I'm in case you are not familiar with SL2C irreducible representations, don't worry. So I'm going to give you some basic fact about it when we, a moment later. All right. Okay, so now we have this boundary Hilbert space. As I said, we are going to quantize simplicity constraint and impose the quantum simplicity constraint to this boundary Hilbert space. Okay, so now how to quantize this? The question is how to quantize simplicity constraint. So and because simplicity constraint is a constraint on B field, so we need to quantize the B field as an operator acting on the Hilbert space. Okay, so the quantization of B field Okay, so these are more or less the same as the quantization of holonomial flux. So this is completely borrowed from the technique is just borrowing the usual quantization of quantum gravity. So we're gonna discretize B field. Discretization. So we introduce B smeared on a triangle F. Okay, so this F is just triangles of or a single triangle of 4 simplex. Yeah, so it is just integrating this B field. B field is a 2 form, so you can integrate on the triangle. You can inspect this action. You see that because of this twist given by the bivariate image parameter, the canonical conjugate variables to the connection field is not exactly B, but a twisted B. So this quantity is the canonical conjugate variable of A. It's not just B. Okay. So the flux operator is not the B, it's not the quantization of B, but this quantity is twisted B. I call it J, BF plus 1 over gamma star BF. Okay, so this is the flux operator act on the Hilbert space. Is quantized. Quantized as the right invariant vector field. On SL2C. Okay, so recall that in usual loop quantum gravity, we talk about SU2 spin network states. And then you have holonomies, and you have densitized triad. Yeah, densitized the triad, and then the densitized triad smeared on the surface give you the flux operator, and then this flux operator are quantized as the right invariant vector field on SU2 group. Okay, and here it's more or less the same, but the group is SL2C. Yeah, so here you have connections gauge connections in F. And as I said earlier, the conjugate variables of this gauge connection is this J variables, which is twisted B. So J and A, they are canonical conjugate variables. So then you quantize this A as holonomies. This is happened in BF already. And then this J is quantized as a flux operator. This flux operator is just the right invariant vector field acting on holonomy. So they are just right invariant vector field on SL2C. Okay, so this J operator it makes sense to be a well-defined operator on the Hilbert space. And then it is convenient to introduce some components. So because J of F, it has IJ index. They are Lorentz Lie algebra valued. But now we can divide this I and J to be a rotation and boost. So 0I, I will call it KIF. And they are boost generator. And JF KL epsilon JKL JF. This is the rotation generator. Because they are right invariant vector fields. Okay, so they are one-to-one corresponding to Lie algebra generator. So you can divide this Lie algebra into divide Lie algebra generators into booster generators and rotation generators. Okay. Now, what is simplicity constraint? Okay, so here we are going to modify the simplicity constraint by discretization and by a modification, what we call the linear simplicity constraint. Okay, the linear simplicity constraint. So you can view this linear simplicity constraint is a discretization and modification of the usual simplicity constraint that I showed earlier. Discretization and modification of B equals to star B wedge E. Okay, and for the details, I'm not going to tell you the details about how to discretize and modify this simplicity constraint to get this one, but the details you can find in the original EPRL paper. Okay, so now I'm just going to state the result for this linear simplicity constraint, which replace the classical simplicity constraint in the quantum replace the classical simplicity constraint and impose to the Hilbert space is this linear simplicity constraint. So it states that for each boundary tetrahedron, there exists a internal time-lag vector I call it Ni, such that for any face, for any triangle, of the tetrahedron, all the B fields, all the star B field should orthogonal to this time-lag vector. Okay. for any of the four phases of a tetrahedron. But geometrically, this is pretty intuitive because you can imagine that consider a geometrical tetrahedron, right? And imagine this B field or the star B field are just the area by vector, are just the oriented area of this of all the phases. Because Bij is by vector, intuitively they are just E by G. They're just E by G, and E by G give you the area, oriented area, or area by vector of the phase. And then because these tetrahedrons are spatial objects, so then there must be a time-like vector which orthogonal to all the phases. Yeah, because tetrahedron is three-dimensional, then there must be a time direction which orthogonal to this to the geometry of the tetrahedron. Okay, so that's the intuition that there exists a time-like normal n such that it's this time-like normal is orthogonal to all the B field associated to this tetrahedron. Yeah, so geometrically it makes sense. Yeah, and indeed you can show that if you discretize simplicity constraint, and the solution of this linear simplicity constraint is also the solution of I showed earlier. All right, so now we can do something further by imposing time gauge, because there's a Lorentz gauge transformation in the internal space. Then you can always make a gauge transformation to make this Ni to be just 1 triple 0. Okay. This gives you another simplification. Now this the simplicity constraint becomes star B 0I f equals to 0 for any f belongs to tetrahedron. Okay, so now this B field is already quantized. Yeah, so yeah, the J field is quantized as a right invariant vector, and then the B field is just a twist of J. Okay, so you can write it explicitly in terms of L and K in terms of right invariant vector field by quantizing this equation, and so this gives you the quantum equation. Well, let's put a quotation mark. Yeah, this operator act on the state psi should equals to 0. Yeah, so this, let's say, quotation mark quantum constraint equation coming from simplicity constraint. Yeah, so this is just by quantizing this B field as a linear combination of right invariant vector fields, and then set 0I components to be 0, you just get this this equation. Basically says L plus 1 over gamma K equals to 0. Okay, and this constraint operator, I will just denote it by CFI. Yeah, so this is the simplicity. Let's call this operator to be the simplicity constraint or linear simplicity constraint operator. And the reason why I put a quotation mark here is that this is not exactly what we are going to do. The reason is that this constraint operator is not first class. Those constraints are second class. So however, those CFI, is second class. Yeah, those constraints are second class, which means that we have to be extremely careful. If we just imposing the constraint like that, we will get very small Hilbert space. This is not really what we want. Yeah. It will be you will get quantum anomaly, and you will have a very small Hilbert space left. Okay, so you can check by yourself. This is indeed second class. You can compute the commutator on the same phase, and what you get is like this: IJK, LK, Okay, obviously on the right-hand side is not anymore a constraint. Okay, so this is not, well, classically this is not vanishing on constraint surface. Okay, so that's why this is a second class constraint. And the way to impose the second class constraint quantum mechanically is tricky. Yeah. So because we have to impose the constraint weakly to impose CFI weakly. Okay, so there was in quantum field theory, there was quite some examples, especially when we talk about gauge theory, electromagnetism and so on. The quantization of electromagnetism has similar problem that when you impose gauge fixing, and then you reduce a first class constraint to second class constraint in electrodynamics, and then to quantize those, you have to be very careful. You have to impose the constraint very weakly, so that in the end you get two polarization of photons. Otherwise, you will get something wrong. Okay, so how to impose constraint weakly? Okay, the way EPRL did is to reformulate those constraints into some first class constraints. So EPRL reformulation. EPRL reformulation. Okay. So originally we have this simplicity constraint. Yeah, so this is a simplicity constraint that we want to impose weakly. And then we reformulate into two kind of constraints. So firstly, what was called the master constraint, just taking square of this operator. Okay, this is the first constraint. And second constraint, but now classically you see this master constraint is already equivalent to the simplicity constraint because this is just a positive quadratic form. And I think you all know what master constraint is. And now classically, this is just a square of the simplicity constraint. And the square of simplicity constraint vanish implies the simplicity constraint vanish. Yeah, classically, this master constraint is already equivalent to the linear simplicity constraint. But quantum mechanically, well, you could consider that, well, I mean, that will be enough, right? And we have master constraint, and we impose master constraint to the Hilbert space, we get a solution, finish. But it turns out that this is too weak. If you only have this master constraint, you will get the Hilbert space, the solution space, too large. And because ultimately we want to embed the amplitude into loop quantum gravity. So which means the boundary Hilbert space should exactly match the Hilbert space of loop quantum gravity, which are SU2 spin networks. So if you only have master constraint, then you have even larger. You have some extra states that you don't really want in loop quantum gravity. Yeah, so which means, and second fact is that in, well, that may be a little bit detailed, but the fact that this is a four-dimensional quantization using bivectors, and which means you have a four-dimensional definition of area by taking the trace of 2B field. You have a four-dimensional definition of area, but in loop quantum gravity, you have already your area operator. And then suppose you want to have the states, the eigenstates of four-dimensional area matches the usual loop quantum gravity area, then you have to also impose something extra, not just this master constraint. Yeah, that's the motivation that there are two constraint reformulating the simplicity constraint. Yeah. The second constraint is actually a quadratic, the diagonal simplicity constraint, CFF. So this is just a star BF dot EF. So here dot x dot y means xij yij. Okay, this is just the inner product in SU2 in SL2C Lie algebra. So then you can write this in terms of right invariant vector field. It is star j dot j square. All right, so this is the way EPRL reformulation. So as I said, as I explained earlier, you can see that there are quite some subtlety in this reformulation. There are about 10 years ago, there was huge literature discussing this kind of subtlety. And you can, if you're interested in the story behind it, you can either look at EPRL paper, or you can look at my paper with Yu Ding, Caloravelli. Number is 10. Yeah. So this paper explained what we mean by weakly imposing the constraint and why, yeah, basically a lot of story behind this simplicity constraint. Okay, so these are the EPRL reformulation. Yeah, and then you can write these constraints in terms of SL2C Casimir operator. Yeah, so that's the convenient part of this this constraint. All right, so of SL2C Casimir. So they are well, quadratic Casimir. Yeah, so there are two quadratic Casimir operator in SL2C representation. Because this is rank 2, this Lie algebra is rank 2. C1 is j dot j. So in terms of L and K, is 2L square minus K square. And C2 is star j dot j. This is minus 4 L dot K. So you can easily see that j dot j and star j dot j, they are just the two invariant bilinears in Lorentz group, in Lorentz Lie algebra. All right, so now you can use these two quadratic Casimirs to re-express two constraints. So firstly, CFF is given by C2, 1 minus gamma square plus C1. Okay, this has to be 0. Yeah, and M, well, MF equals to 0 gives you L square 1 plus okay. So the interesting part here is that it also relates to the quadratic Casimir of SU2. L2, this L square is just a quadratic Casimir of L2 of SU2. Yeah. Yeah, it shows the idea of simplicity constraint that you want to reduce your Hilbert space to, in the end, to SU2 spin networks. Okay, so this is the second equation. You can plug in the first equation, solving, for example, C1, and then plug in the second equation, what you get is C2 hat equals to 4 gamma L squared. Okay, so let's call this equation star. So this just combining the previous two equations, you will get this star equation. All right, so now let's, because they are quadratic Casimir's, C1 and C2, they are quadratic Casimir's, and for any irreducible representation of SL2C, these quadratic Casimir's are just constant, a constant multiple of identity operator on any irreducible representation. So now let's look at the irreducible representation of SL2C. Unitary irrep of SL2C. I'm going to introduce some basic facts which are sufficient for our purpose. So more precisely, I'm going to talk about the principal series. Principal series of irreducible representation. Okay, so for any principal series or unitary irreducible of SL2C, the carrier space is infinite dimensional. It's a Hilbert space. Why it is infinite dimensional? Because SL2C is a non-compact group. SL2C is non-compact group, then any unitary irreducible representation of a non-compact group is always infinite dimensional. They are truly Hilbert space. That's different from SU2. So the Hilbert space is, I call H, rho, and N, is infinite dimensional. Dimensional Hilbert space. And the representation is labeled by two parameters. Rho belongs to real. Rho is a real parameter, and N is a positive integer for 0. Okay, it's just like it's quite analog with SU2 representation in that sense, because SU2 representation is labeled by spin J, half integer spin J. And so here now the SL2C unitary irreducible representation is labeled by two parameters, rho and N. Rho is continuous, N is discrete. Okay, and how to understand this representation? You can look at the representation of the subgroup, because we know that SU2 is a subgroup of SL2C. Okay, so then any representation of SL2C is also a representation of SU2. Okay. So which means that this Hilbert space, it is also a representation space of SU2, but it is not anymore irreducible representation. It will be reducible representation. So which means that H, rho, and N is reducible by SU2, by the subgroup SU2. Okay, so which means that the Hilbert space rho and N, H rho N can be written as the direct sum of SU2 irreducible representation Vj. Okay, and it must be infinite many copy of SU2 because SU2 representations, because H is infinite dimensional. The left-hand side is infinite dimensional, so the right-hand side is also, right-hand side should also be infinite dimensional. So, but SU2 Hilbert space is finite dimensional, so therefore it must be infinite many copies of SU2. And then there's also a starting point of this tower, which relates to this N. So J has to be starting from N half, all the way it goes to infinity. Okay, and with multiplicity only 1. So any SU2 irreducible representation only happen once. So this is the fact that I'm not able to explain here. Okay, so just accept this result. Yeah, and this is take it as a fact. And then once you have this decomposition, you can write down the canonical basis. So there's a preferred basis. Preferred means that compatible to this direct sum decomposition, what we call a canonical basis. So firstly, it is labeled by rho and n, labeling the representation of SL2C. And then the third label is that this state belongs to which copy of this SU2 this state is belongs. Let's say this is J, is in copy J, and then there's also inside this SU2 hyperspace Vj, there is also a magnetic index. So labeling the basis inside this region. Okay, so this is what we call canonical basis. This canonical basis is compatible with the composition of SL2C irreducible with SU2. Okay. Now, as I said earlier, the quadratic Casimirs are just constant multiple identity operator on irreducible representations. So quadratic Casimir. Now they are just taking constant values on irreducible representations. C1 is given by 1/2 n square. They are just you see, they are just functions of n and rho. C2 is just given by n times rho. Okay. So these are again some basic facts of SL2C representation. Now you can plug in this formula into those constraints. Now you have the value of C1 and C2. You can just plug in the constraint. All right. And also, okay, so here you get C1 and C2, and now this L is evaluated. This L is just SU2 Casimir, and they are evaluated inside each copy of this Vj. So you see this constraint, for example, the star constraint, it tells you you need to pick up one single copy of SU2 irreducible representations in this tower. There's only one copy of SU. There's only one possible J in this tower can satisfy this star constraint, because this is a relation between SL2C Casimir and SU2 Casimir. Okay, so maybe I should just write down the result of those equations. So the first constraint, CFF equals to 0. This gives you the equation between rho and n. You just plug in the result of quadratic Casimir, you will get this. Okay. And then the star equation, the star constraint gives you n times rho equals to 4 gamma j plus 1. So as I said earlier, there's not all the j's can satisfy this constraint. So you see you get this tower j from n½ all the way to infinity, but there's only one j in this tower can satisfy the simplicity constraint because of the star equation. Okay, so now you can plug in this equation into Mathematica, for example, and then just solve n and rho. Okay, so you will get the solution of n and rho. So you will get rho equals to 2 gamma j. Okay, 1 plus some order. You will get not just 2 gamma j, but some other factor, but these are of order 1 plus 1 over j, and n equals to 2 times j, 1 plus order 1 over j. Okay. Yeah, basically you get the solution and you expand in terms of 1 over j. Okay. So now you see that once you have a SL2C unitary irreducible representation, you get the data for rho and n. It determines a unique j, satisfy this constraint. Or the other way around, if you have j, it determines a unique SU2, it determines a unique SL2C irreducible representation. Yeah, rho and n depending on j. And to construct the model, so since it doesn't affect semi-classical limit. It's not. Because the semi-classical limit is just one large limit. Yeah.
So is it possible? So the question is like, because n needs to be an integer. So if one plug equation in that sense.
No. You see, this is something I'm going to explain right away. So you see, n equals 2 times j. It can only be satisfied by the lowest level in this tower, right? So it starts from j equals n half.
Okay.
So which means that the second equation level or a few levels above, yeah, and you will get some corrections to this solution. Yeah, sometimes it's possible, but the price to pay is that you are going to have mismatch between the area operators of 4D and 3. That's why that area operator, the matching of the area operator is kind of important to select just the lowest level. Okay. All right. Now, this is the solution of the simplicity constraint. So as the result, what we get is what I would call EPRL projection. Yeah, it means that we project out all the states inside this irreducible representation except the lowest level in this Hilbert space. Right. Okay, so first ingredient is that so we restrict the principal series representation to be those satisfy the constraint. Restrict principal series EREP to be rho f and f. Remember, for Spinfoam, every representation is associated with is associated to a phase. So the representation is labeled by f to be 2 gamma jf 2 jf. So we only look at those irreducible representations. And secondly, so we introduce an important ingredient called Y-map. Just making so make it as a mathematical structure. So this Y-map is given by an embedding from SU2 irreducible representation into SL2C. Okay, into those ones satisfy the first condition. Yeah, and this embedding is very simple because this SL2C irreducible representation can be completely reduced to SU2. Okay, so this is K from JF BK. Okay, and this embedding is just given by identifying just by to the lowest level. Okay, it just this map just identifying Vj to the lowest level in this infinite tower. Okay, and this is more explicit in terms of if we write in terms of canonical basis. So for SU2 representation, the basis is J and M. Yeah, it maps to the canonical basis in SL2C, 2 gamma JF, 2 JF, JF, MF. Okay, so this is give you an explicit formula for this Y map. Okay, so this give you these two ingredients is the EPRL projection and tells you what is the physical state after imposing the simplicity constraint. Now let's define the EPRL intertwiner. Okay, so the reason is that remember the Hilbert space of boundary BF theory, they are given by SU2 irreducible SL2C irreducible representations and also SL2C intertwiners. Okay, so here now we have the restriction of representation, but we also need a restriction of intertwiner. Okay, but the restriction of intertwiners can be just induced from this Y map. Okay, so this is the restriction of SL2C intertwiner. Yeah, and the result of the restriction are those EPRL intertwiners. Okay, now given SU2 intertwiner, it turns out that all those EPRL intertwiners are just determined by SU2 intertwiners. Okay, so let's first pick up a SU2 intertwiner. Let's say we are 4-valent. The intertwiners are always 4-valent. Okay. Now, firstly, we use 4 copies of Y map act on this intertwiner. Okay. So now what we get is just a tensor. It's a SL2C tensor. Okay. Because Y map act on SU2 state, give you an SL2C state. Yeah, and then you get 4 copies of Y map, then it is a tensor. Okay, but not yet a invariant tensor. But what we want is a intertwiner. Then what we can do is making a projection. So let's say making a projection onto the intertwiner space of SL2C. So this is EPRL intertwiner. Okay, and this P is a projection onto SL2C intertwiner space. Okay, so this is the scheme. All right, it defines, give you a formal definition of EPRL intertwiner. Now we can write this intertwiner in a more explicit formula. I will try to make it more and more explicit for this construction explicitly. Okay, let's use, let's write this intertwiner in terms of SL2C Wigner D matrix. So this is SL2C Wigner D matrix. So what is D matrix? It's just a representation matrix or representation operator. Yeah, let's say representation, infinite dimensional representation matrix, because now representation is infinite dimensional. This is given by just the matrix in the representation. The matrix of representation of G in canonical basis. Okay, so for any G belongs to SL2C. Okay, so this is the Wigner D matrix. Now I can write this write explicitly this EPRL intertwiner to be a SL2C integral. This integral just is a group averaging, give you the projection operator onto SL2C intertwiner space. Or the gamma J I. Now this Wigner D matrix is acting on, it's a representation matrix, but now this is acting on a SU2 intertwiner. Okay. So this is the explicit expression for the EPRL intertwiner. Okay. Some explanation, you can notice that this J and this J is the same, right? And this just shows the Y map. Yeah, it picks up the lowest level in the representation space, and this M is contract with this M, right? This means that this representation matrix is acting on SU2 vectors. So this contraction, yeah, with Y map. Okay, so it shows that firstly you have Y map, embed the SU2 tensor into SL2C, and then contract with a Wigner D matrix, means that you have group acting on this tensor, and then you integrate over SL2C. This gives you a projection operator onto SL2C intertwiners. All right, so now so we have this EPRL intertwiner. Remember that whenever we construct the Spinfoam amplitude, one formulation that we can use is associate every edge a projection operator. And then we take a trace of all those projection operators, we get the Spinfoam amplitude. Right? And remember last time we talked about BF theory, we formulate in this way. So now we can define the edge projector. Yeah, let's put a quotation mark. PE is just given by sum of EPRL intertwiners. Okay, and now this sum is sum over all the SU2 intertwiners, because every EPRL intertwiner is determined by SU2 intertwiner. Okay. So these are SU2 intertwiners. Okay, it means that for any edge, so the same logic as last time. So for any edge, we associate starting point or the starting half edge with a intertwiner, and the endpoint or the second half edge, the star of the intertwiner. So this is edge E. Okay, and the reason why I put a quotation mark is that this guy I write it here is not precisely a projection operator up to a certain issue of normalization. But the EPR, people work on EPRL model always use this, although this is not precisely a EPRL, precisely a projection operator. And the detailed discussion, you can look at the KKL paper. KKL paper. KKL means Kaminsky, Kieslowski, and Lewandowski. So these are, they have very nice paper in 2009 on reformulating EPRL framework or Spinfoam framework in a beautiful language. Yeah, and it would be nice that you can check them out. And one of the paper and the second paper discuss this edge projector and showing that this way of this PE here, I write here, is not precisely an edge projector, but some certain modification or normalization of the projector will give a true edge projector. But so far, right now, I'm still using this PE to write down the amplitude because this is simpler. Now, okay, so then we can write down the EPRL spinfoam amplitude. From amplitude by just formally write as a trace of edge projectors. So now this amplitude is on a simplicial complex. JF, and write formally as a trace of all these quotation mark edge projectors. Okay, so this is quite implicit. Yeah. So to make it more explicit, let's go to the different representation similar to BF. We can extract the vertex amplitude from this formulation, and it is indeed what we want to do because yeah, in the spinfoam quantization, we quantize the theory in a single four simplex, yeah, and then develop the spinfoam amplitude on the simplicial complex. Okay, so now we can use this formulation to extract the vertex amplitude. Okay, so let's look at a single vertex with 5 spinfoam edges. Yeah, and now let's say all of these edges are outgoing. Okay, so then from the picture above, you can see that the begin half edge associated with the EPRL intertwiner. Okay, so now we can, so here now, which means that for each vertex amplitude, you have 5 EPRL intertwiners. Yeah, and remember that it has to be contracted. So for any 2 edges, there's a phase, and then for any phase, there's a contraction of intertwiners, just like we studied BF theory last time. So now we can write the vertex amplitude AV to be the trace. And the here trace means certain contraction according to the phases of 5 copies of EPRL intertwiner. Okay, so this is the vertex amplitude. And then the EPRL spinfoam amplitude is given by sum over all the spins on the face, all the SU2 intertwiners on the edges. Yeah, there's a phase amplitude, but this phase amplitude is a choice for EPIL, and there was some discussion on that. Yeah, you can search, for example, phase amplitude, Spinfoam amplitude, and you will find the article discussing why we have to choose dimension, SU2 dimension, to be the phase amplitude. And then product over all the vertices. And product the vertex amplitude. So this is the EPIL Spinfoam. But the states are always SU2 spin networks. So the states summed are always SU2 spin and SU2 interplanar. And the vertex amplitude are functions of SU2 spin and SU2 interplanars, yeah, because they are constructed by using EPIL interplanars. Yeah, so which means that this amplitude can be perfectly embedded into the framework of kinematics in loop quantum gravity. So this defines the dynamics of loop quantum gravity states, which are SU2 spin networks. All right, so this is, you see this formula is still a little bit formal. Now I'm going to write down the formula which are more explicit for vertex amplitudes. So let me give a more, let's say, more on the vertex amplitude. Okay. So now, so let me write the amplitude using SU2 states and Y map. Remember that they are SL2C. So there is this SL2C integral for each EPIL intertwiner, right? So now we have 5 EPIL intertwiner. So in principle, we have 5 copies of SL2C integrals to 5 DGA. Okay. And then we have those intertwiner contract to each other. Yeah. We have this contraction, but the contraction are going respect to all the phases, and they are 10 phases. Okay. So now we have product of A smaller than B. So for all the pair A and B, with A smaller than B, you get all the 10 phases. So by combinatoric number. All right. And then you can write the contraction as the inner product. So this inner product is, yeah, let me just write it down. So this inner product is inside is for the SL2C irreducible representation, but for the states, which are the image of Y map. Inverse GB Y map. Okay. Okay. So now it means that we have SU2 states, and first you use Y map. Okay. And then you transform using SL2C group using this GB. Yeah. And then contract with another state using, well, here you see MAB and MAB and MBA. They are 2 different magnetic quantum numbers. Yeah. And so there are 2 SU2 states associated with the phase labeled by A and B. So it's like you first have the states, you use Y map embedded into SL2C, and then you use group transform those, use SL2C group element transform these 2 states independently, yeah, and then make a contraction, yeah, making inner product. And then you integrate over all the group elements to make the group average to get intertwined. So this is the explicit expression for the vertex amplitude, and you can make it even more explicit by using the Y map, by using the definition of Y map. Because it's just by using canonical basis, the Y map maps SU2 states into canonical basis of SL2C. So it is 2 gamma J AB. And this is the explicit, let's say more explicit expression, better explicit expression for vertex amplitude. But there is a subtlety here, which is that this amplitude right in this way is actually divergent, because the integration is over SL2C. This is a non-compact space. So you can imagine that there's a danger of divergence. And indeed, this amplitude written in this way, it is divergent. But fortunately, the divergence is coming from a gauge transformation. Gauge transformation. Okay. As you know that for gauge theory, there's a gauge transformation, and this gauge transformation is a redundancy in the path integral and may cause the divergence. Yeah. And fortunately here, it is very much the same. So gauge transformation is, you can easily see that the gauge transformation is just given by this. You can multiply on the left any group element GA by any X belongs to SL2C. Okay, so you see that this combination is kept invariant by this gauge transformation. So that's why this is indeed a gauge transformation. So these actually cause the divergence. Divergence of AV, of the amplitude. Now the resolution is very simple. You just make the gauge fixing. Gauge fixing. Gauge fixing is just fix the integral. Just remove one copy of the integral. Basically, it's just removing one copy of the integral. 1 to 5. By gauge fixing by inserting a delta function. And inserting a delta function of, for example, G5. Okay. And then the result is finiteness. AV is finite. Okay. You can check out this paper for, well, there are 2 papers about this. So these 2 papers shows that this once you make this gauge fixing, the resulting amplitude is finite. All right, so this is basically the definition of the EPIL vertex amplitude, and also some more explicit formula for this vertex amplitude. Okay, so now how to use it? Well, to use it, let me discuss. Let me see. Okay, So I think there is less than half an hour right now. So I'm not going to cover the application of this amplitude, but I can give you some, give you another representation of the amplitude, which may be helpful to understand better the model. Okay, so let me. The next thing I think I should talk a little bit is the coherent state representation. Coherent state representation of the vertex amplitude. Yeah, and why this is helpful, because this, so here it is already quite explicit for this formula of the amplitude, but still it's written in terms of form and some abstract inner product of SL2C irreducible representations, right? So now to actually do computation, you have to make this formula, make this integral even more explicit, to actually write down explicit formula of this inner product as some L2 type integral, right? And this can be done by using and conveniently doable in this in the coherent state representation. And that's why this is very useful to actually study the amplitude. Okay, so now what is coherent state? So let's look at a SU2 irreducible representation. Okay, so this SU2 irreducible representation, of course, this is acted by SU2 group. Okay, and you can look at the highest weight vector. Highest weight. So here I'm going to define the coherent state in SU2 representation. Highest weight state. Well, this state is just J and J. The magnetic quantum number is J. It means really the highest weight, highest vector in this representation space. Now, what is coherent state? This is coherent state is written by J and Kc. Okay, and this Kc is a spinor, is a two-component spinor, and how this state is defined is given by a SU2 group element determined by Kc, Kc0, Kc1, and minus Kc1 bar, Kc0 bar. And then this SU2 element acting on J and J, act on the highest weight vector. So here, this here I write this triangle. That means that this group element is acting on the state. Okay, so you see the SU2 coherent state is certain SU2 group element, certain class of SU2 group element acting on the highest weight vector. Okay. And here this Kc is a spinor, Kc0, Kc1, satisfying the Hermitian inner product of Kc is normalized. So this Kc is normalized with respect to the Hermitian inner product. Kc0 bar, Kc0 plus Kc1 equals to 1. Okay, so namely this Kc is normalized. And what is the geometrical interpretation of this coherent state? Okay. So you can imagine that J, this is highest weight vector, can be understood as a vector in z direction, because this is the J3. This is the eigenvector of J3 and with the largest eigenvalue. So you can view this is a vector in z direction, in the 3 direction. And then this J Kc, so being a SU2 group acting on the highest weight vector, this is a rotation of this vector. So it describes a rotation of the vector from z hat to a arbitrary, well, to a different direction. Let's call it a unit vector n of c. This n is dependent on c, and this n is given by this n c is given by c Pauli matrix c. Okay, so if you can see that this coherent state can be seen as a vector, the quantization the quantization of a vector in 3 dimensions. Quantization of unit vector in 3 dimensions. And relating to Spinfoam or discrete geometry, so this n c is the three normal of a tetrahedron phase. Because remember, for Spinfoam, every representation is associated with a phase. So which means every state in this representation associated with a phase, and this phase belongs to a tetrahedron. Okay, so you view this geometrically, you have a phase, you have a triangle, and then this n c is just the normal vector, the unit normal vector of this triangle. All right. So now you can, once you have this coherent state, you can define a coherent intertwiner just by group averaging. Again, this is SU2 intertwiner. Coherent intertwiner. All right. Okay, so these describe a semi-classical tetrahedron. Yeah, because now you have 4 copies of these normal vectors, and C1, you have another normal vector, and C2, and so on. You have 4 copies of this vector and get group averaged. Yeah, and you can. There was a study of that, 07, 05, 6, 7, 4. So this is the paper study this coherent intertwiner, and one shows that this is also a coherent state picked at the point satisfying the closure condition. So picked at the data satisfying the closure condition. Yeah, I'm having this closure condition means you can reconstruct the geometry of tetrahedron. All right. Now let's look at coming back to the vertex amplitude. Okay, but now I want to use the coherent state J and C to express this vertex amplitude. Namely, before I'm using canonical basis, and now I'm using coherent state basis. GA delta G5. Yeah, so this is a gauge fixing. Smaller than B. So now I'm using coherent state. Okay, so now this inner product. So this inner product is for SL2C unitary irreducible representation. Okay, so now there is a basic fact for this unitary irreducible representation is that this rho n, this representation space belongs to the space of homogeneous functions. homogeneous functions of two complex variables, z0 and z1. Okay, so this I will call that. Namely, the functions satisfy the scaling property, certain scaling property, f. So this function is z and z bar, but satisfy the scaling property if you scale lambda by lambda, those z and z bar with lambda and lambda bar, it's the scaling exponent relates to rho and n. So it's the lambda minus 1 plus half rho I rho half n, and lambda bar minus 1 plus. So this is the basic fact of well, basic way to representing this Hilbert space. Okay, and now on this Hilbert space, you can the inner product is actually an L2 inner product of these functions. Okay, namely f prime. These two homogeneous functions can be written as an integral with certain measure of z bar and f z bar, f prime z bar. Okay, and this integral, the integration measure, is given by this. Z1 minus Z1 d Z0 wedge. Okay, and you can check that the integrand here I write above as a differential form. It is scaling invariant. If you scale every z bar by lambda and lambda bar, so you can see this quantity is actually scaling invariant. It means that this integral is actually carried out on projective space CP1. So you can check by yourself that indeed this integral, the integrand is scaling invariant, and this integral is actually on CP1. Okay. So this is a way to representing the Hilbert space as an L2 Hilbert space of homogeneous functions, and therefore you can compute the Y map of the highest weight vector of SU2 to gamma j to j. So this is this canonical basis. This is the state corresponding to a homogeneous function, and the result of this homogeneous function is given by this dimension j divided by pi. The nice thing of that is it has two factors. One factor is just making up the scaling property, and the other factor is completely SU2. Okay, so the second part, it is just an SU2 state written in terms of that, yeah, because SU2 Hilbert space is a homogeneous function, but also holomorphic function. So holomorphic homogeneous functions actually gives you the SU2 representation. And now for SL2C representation, it is only the homogeneous function, but not holomorphic. But you see, to make up the scaling, you just multiply the SU2 part by a part of the norm of that bar with certain scaling property. Yeah, the second, this factor is just give you the right scaling property. Then you can also compute the the coherent state, the Y map of coherent state. Yeah, and this is just given by, you see, coherent state is the SU2 action on the highest weight vector, which means you just act on the state above by certain SU2 relates to Kc, and you will get this. J. Okay, so so all the inner product I write is they are Hermitian inner product. So these I will call it F of Kc. Then the inner product happened in the Spinfoam CAB Y dagger GA inverse GB. BA is just given by this CP1 inner product prime F CAB. So now the group element, the group action on this function. So it's the same as it's given by the trans Z. It's complex conjugate in F. So here, little t means transpose. Okay. Now we have the explicit expression for this function f, this homogeneous function f. Now we can just plug back in the amplitude. Okay. Then the next step, you can just plug in the formula. So you get pi dimension JAB integral CP1 and then bar GA dagger Z bar EB, okay, CAB. Sorry for so many indices. It's actually not that complicated. All right. So now you see you got really an explicit expression for the amplitude, at least for the inner product in the amplitude. Okay. Now you can actually write it as a something similar to path integral. Okay, so this is CP1 integral and certain integration measure. I call it dz, which is different from omega, and exponential of some action labeled by AB, because this is a single inner product with respect to phase. Well, to write this action, you just write the integrand as exponential, which means this action is just a log of the integrand. Okay, so you can this action is so yeah, okay, so this, let me first write this dz is just it is a homogeneous homogeneous measure of degree 0. So it's a scaling invariant measure. ZB, ZB, ZBA, ZBA. What are these? Are capital Z's. Capital Z is AB is given by GA dagger Z bar, and ZBA is GB dagger Z bar. Okay, so this give you a scaling invariant measure. And what is this action? This action is just given by 2J AB logarithmic A. So except this you see this -1 factor, the -1 exponent are responsible for this denominator. So apart from this -1 on the exponent, if you log the integrand, you just get this action. Okay, so now you can, so for any inner product, you can write it as an integral of certain exponential of action. Now this vertex amplitude also has a path integral like expression. JAB product of all the SL to Z integral. And now you have a product measure of spinors Z, gauge fixing, and exponential of the total action. Okay. Now this total action is just the sum of all the phases of each SAB. Okay, I think my time is over. I think this is a good time to stop. So you see, we end up with maybe this is so far the most explicit expression for the spinfoam amplitude. Yeah, and it's very easy to it relates to the action principle, and it is so it is easy to study semi-classical property. Yeah. And it's precisely happening here is that this action, you see this action is linear in J, and if you scale J to large, and then it will be just like this J behave the same property like 1 over H bar. And if you scale J to large, it corresponds to H bar being small. And then you can use the stationary phase analysis to study the semi-classical property of the spinfoam amplitude. And it was indeed what has been done in many semi-classical analysis of in many studies of semi-classical analysis of spinfoam amplitude. Okay, I think I should stop here. I hope you all enjoy this spinfoam lecture. Any